Okay, so now we're moving into 10.3 of the chapter. So we're sort of looking at now the types of graphs that there may be. So your textbook comes with this nice little table which gives 3 different types of graphs. So just reading through it, I know, maths in real life, who would have actually thought? So we've got simple graphs, so no loops or multiple edges. So if we had this graph up here and we added in an extra edge here, or we created a loop up off of this vertex, would no longer be a simple graph. Like the name suggests, it is simple. So that's looking at things like roads connecting towns. Yeah, pretty simple application there. So a complete graph has every vertex connected to every other vertex. So like sporting teams who would have to play each other, things like that. So particularly, you know, in sporting comps where they're making sure that it is fair, that every team does play every other team, perfect application. Then we move into a subgraph. So that's looking at where they take part of the graph and just represent it like that. So as you can see, this contains some of the information from this graph. So not all of it, but it is the same. So J to N, J to N, N to K, N to K, K to M and K to L, K to M and K to L. So they haven't changed any of the information. They've just selected particular parts that they want to display. So let's work through some of these questions, because what the exam questions might do is ask you to represent it in the type of graph that would be used to display the information. So if they give you a bunch of sporting teams, they're going to say, which graph would you use to complete this kind of application? So let's go through and look at some. So we've got a local soccer club. It's having a round robin competition. So every other team plays every other team. 5 teams in the competition. So of course you're going to need to use a complete graph, because you're going to want every vertex to connect to every other vertex, so every team to play every other team. So the edges, those connections are going to represent those games. So remember we were given this formula in that original table, which told us that the number of edges is equal to n, being the number of vertices, multiplied by n minus 1 divided by 2. So that will give us the number of edges, and the edges in our graph will actually represent the number of games. So when we draw it, you'll actually see how that comes to play, but without drawing it, you can calculate the number of games that will need to be played. So E is equal to this formula. So I'm just going to plug in the information. So we know that there are 5 teams, so there's going to be 5 vertices. So it'll be 5 multiplied by 5 minus 1 all over 2. Awesome. So we just work that through. So 5 minus 1 gives us 4. 5 times 4 is 20. 20 divided by 2 gives us 10. So I'll write out the steps so that we've got that. So all I did was go 5 minus 1 gave us 4 over 2. So 20 over 2, which gave us that 10. So there'll be 10 edges, therefore 10 games will have to be played. So that gives us question A and question B there. So question B was this part. So now it wants us to check our answer by completing the graph. So all I'm going to do is, I know that there are going to be 5 vertices because there are 5 teams. So I'm just going to go ahead and draw 5 vertices. They don't have to be arranged in this shape. You could arrange them however you feel. And remember that they do have to connect. So each vertex has to connect to all of the others, like so. So just go ahead and draw in those edges. So I'm just working through systematically, working my way around. and connecting them all. So that's the complete graph. So I'm going to go through and count my edges just to make sure that it does match up. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've counted 10 there, but I'm going to actually draw over them so you can see that more clearly, because I think that's a bit confusing with the overlapping edges there. So because there's no vertices in here, these aren't each little sections of edges. The long line is the edge. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 edges equals 10 games. So that's an example of a complete graph.